need every bit of it down, and I am going to add it to yours. Okay, this is very nice. Go.
Sorry, I didn't know. So does everyone understand why our bounds here go from negative R to R? That's the first step that we need to make sure everyone has. Because if we have a circle and we center it at the origin, the bounds are going to be from the negative radius to the positive radius. That's going to determine the size of our circle. And then we have our basic formula for pi r squared. Here we're using the same r squared minus x squared. We should all be okay with that square root. That's what we just found from the circle formula. Everyone with that? Okay, awesome. So we're going to move here. So we pull our pi out in front. So we're going to have pi. We still have our same integration bounds. And then we're going to square the square root, which is just going to get us back this main number with just a normal power of 1. Everyone still good with this part? Okay. I'll take it down. Okay. So from here, we're going to take the integral. Can anyone tell me what the integral of r squared is going to be? Let's be careful, because this is with respect to x. Remember, r squared is actually just going to come up being a constant. So who knows what the integral of r squared is going to be? R squared x. Great. So this first part's going to go to r squared x.
Who said that? Jordan. Who said that? Really? You're Bria. No, not because I'm surprised. It's about time you talked a little bit today. Okay? You try to hide in them.
Continue, Morgan. We're good.
Okay. It doesn't change. Okay. So r squared, if we take the integral, we're going to get r squared x. And if we take the integral of negative x squared, we're going to get negative 1/3 x cubed. Which is what we have here. And we're just going to look at this, and we're going to evaluate it from our bounds of integration. Is everyone still good with this? Our limits of integration. We're going to evaluate it there. Everyone's still good with this? Okay. The next step here is to plug things in. So we're putting r's in for x's and negative r's in for x's. Does everyone understand why we're doing that? Because it'd be the same way as if there weren't any r's in there and we were plugging in 3 for x. Or like we just in the last example, negative 2 and 2. We put the r's in for our x's. So we're going to have pi r squared times positive r minus 1/3 r cubed. And then minus all of this evaluated at negative r. So if we put in negative r, that's going to give us negative r cubed plus r cubed over 3, because we're going to have 2 negatives. So is everyone good with this line right here of what happened, how we got this stuff? When we plug in r and negative r for x.
Give them a moment, Morgan, because they need to understand that. They know that they're doing a fundamental theorem of calculus, but I need you to follow the plug-in. It's no different than our ln4 minus ln5, something like that. It's not anything different. It's the same idea.
So it's the same even if we were to have to put a completely unrelated variable in there, or we were to put the number 0 and all of it could go to 0. It's the same exact process, but we just need to make sure that we don't confuse the fact that just because there's already r's in there, doesn't mean we can't add additional r's in for x's and things like that. So we just need to keep our variables pretty straight. And what my calc teacher now actually does is put at the end of these, he writes x is equal to r, x is equal to negative r when he plugs things in, because when you get to have more variables, it's important to keep your bounds straight for each one. So if that helps you to remember, if you have a lot of variables and you're putting in variables for bounds, I would recommend that set if that makes it more clear for you.
And that's called multivariate calculus.
Yeah, agree. Okay, I'll take it.
Wonderful.
Exactly. So we're going to continue with the simplification here. So we have r squared times r, that's gonna go to r cubed. We have r cubed times negative 1/3, that's just gonna stay the same here, minus. And then we have negative r times r squared, so that's gonna be negative r cubed plus r cubed over 3. And we're gonna distribute our pi's between this term and this term and this term and this term. Every term is going to get a pi. So the really cool thing about a volume of a sphere, as you guys can see, is it all comes out, all of our terms end up being a certain constant or a scalar times pi r cubed. So we can just add these scalars basically here when we pull out our pi r cubed. So we're going to make sure we get a pi in all these terms, because I'm missing a pi right here, but it's right there, so you can see that. And we're going to look at what the coefficients of these are. So if we pull out a pi r cubed, because every term has that pi r cubed.
And look at the factoring, give them a moment, we're gonna pull that factoring out, pull out pi r cubed, so they can see what they have left over, because they're factoring.
Exactly, you want to make sure you pull out all your like terms so that, because no one would memorize the formula for a sphere if it were that long. You know what I mean? Make sure you have all of your terms combined and factored properly. So, does everyone see how pi r cubed was distributed into all the terms to start with, and then how it's being pulled back out? Any problems there?
So they should be able to get the final answer. They should be punching it in again. Sam, I see you punching, so give us the final answer in a minute.
I got 4/3 pi r cubed.
Exactly.
And have you ever seen that before?
I don't think so.
Where?
I said I don't think so.
You don't think so?
Where am I? Oh, shoot. Yeah.
Is what?
It's a volume.
Yes, sir. In the 7th grade.
Exactly.
And this is actually the proof for that formula. So all you did years and years ago was take the formulas you never thought, where is that coming from? Here you go, here you go, here you go, here you go. And that's why I'd say Caroline, who's beginning to love calculus. She is. She wrote that in her IA, Sarah. At the last piece of her IA. That calculus is beautiful. It ties together everything you've already always learned in math. It brings it all together. You guys didn't even notice her say scalar. It should have clicked for somebody. Oh no, vectors are in this. Yes, 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 yes. All day. So even this formula, this elementary formula that you were given years and years ago, here's your proof. And it should be your proof. When you start revolving an area around an axis, yes, you create a volume, and yes, every one of your volume formulas come from integration. Now, please don't think that your formula came first. No. Thank you. I just had to get on that soapbox. You know that.
So for anyone who didn't see what happened here, when we pulled out pi r cubed, this term was 1, this term was negative 1/3, this term was 1, and this term is negative 1/3. So 1 plus 1 is 2, minus 2/3 is 4/3 pi r cubed. And just to double check, we took our known formula of, we can take the formula we know to be 4/3 pi r cubed, and we can check to see if, for the last problem when we got 2, if this formula would uphold for that as well. We can do 2 cubed, so that'd be 8, times 4 would be 32, over 3, pi. And
Nice.
that's what we got from the last question as well. So it's like, yeah, all of this comes together. You would have gotten the same thing if you were in 7th grade, but you wouldn't know where you got it. That's pretty cool because you can take, so it depends on your level of skill when you learn things, but you don't have to take anything that anyone tells you to be for what it is. In the back of the textbook, there's like a large section of proofs, and you can just look through them if you want. And everything that you're taught in math class, you can prove. You don't have to take anybody's word for it. Sometimes like language teachers be like, oh, you got this deep interpret meaning. You're like, nah, I don't think so. It's the same thing. Here you can prove it. It's not like you don't have to take someone's word for it. So this is going to be the most complicated problem we do.